Welcome to Brain Vision.
Okay, so let's see how best we can prove this equation. Okay, now we've been asked to prove an equation of the force per unit area to be equal to the Young's modulus into bracket times the change in length over the initial length minus the coefficient multiplied by the change in temperature. All right, so let me put that down. So it's equal to Young's modulus into bracket change in length divided by the initial minus the coefficient multiplied by the change in temperature. Okay, so we are to look at this, how best we can solve this. Now, this is actually a brass rod fixed between two ends. Now, due to change in temperature, it undergoes some sort of expansion. But then we also need to take into consideration that this rod is also fixed to two ends. It's fixed to two ends. So even though as there's some sort of tensile stress inside this rod, the expansion due to the change in temperature is also another effect inside the system. All right, so we want to see how this tension and then the change in length could be related in an equation. Now let's take a look at that. Now, first and foremost, since we are considering temperature change, let's look at the change. Let's consider the expansion inside this rod. So, picking the equation delta L is equal to L naught times the coefficient times the change in temperature. Let's say this is our equation 1. All right. Now let's also consider the tension, which could also affect a change in length of that rod. So if we consider the tension, considering tension, all right, we can see that the change in length, considering tension, is equal to F over A multiplied by the initial length divided by Y. Now, this equation that I'm talking about, I picked this equation from Young's modulus. From Young's modulus equation, where we have Y to be equal to the force over the area plus the stress applied over the strain. So delta L over L naught. Okay, so that is where I'm getting this from. So in the sequence of making this the subject of the relation, that is how come I have this. Okay, so let's move on. Let's move on with this. Good. Now, once we have this, we can say that the total change in length, we can see that L total, the total change in length is equal to the total change in length is equal to the change in length of the rod due to temperature, and then change in length due to tension. So tension, let me say T subscript F, or let me say delta L subscript TF, which stands for tensional force. Okay, so when we look at this, we can put all of these equations together, and we'll say we'll get this L naught multiplied by the coefficient and the change in temperature plus the force, the force times the initial length, all divided by the area times Young's modulus. Now let me put all this into bracket. Good. All right. So we are looking at the change in length. So let me factorize the initial length out. So I have the change in length total. Change in length total, all divided by L naught. And we will see why all over L naught. So this will leave our equation into bracket, coefficient times delta T plus F over A multiplied by Y. Okay. All right. So this is where we arrive. Now, our equation is supposed to conform to what we have here. All right. So we are a bit close. So let's see how we can leave the equation in the final stage. Okay. So if we have this, we can say that the Young's modulus into bracket delta L over L naught minus coefficient times the change in temperature is equal to F over A. Okay, so all I have to do is just to make the F over A the subject, which is the stress, the subject, which is the stress, the subject. All right, so F over A is equal to Y to bracket change in length total, but let's forget about it for the sake of space, minus the coefficient times the change in temperature. All right, so basically this is what we are looking at. This is what we are looking at. Now let's look at the B part of the question. Now the tensile stress in the wire is what we want to look at. Is what we want to look at. Okay, so we know that Ti, that's the initial temperature, is 20. It's 20 degrees Celsius, and then the final temperature, T subscript F, is 140 degrees Celsius. 1 degree Celsius. So let's go ahead and use our equation. So let's first and foremost calculate that. Let's put this equation into the equation. All right, good. We can then say that F over A, let me scroll up, is equal to Y into bracket L naught delta times T. I beg your pardon, let me get this right. Over L naught minus the coefficient times this. Good. All right, now we have F over A is equal to Y times delta T multiplied by coefficient of B, the brass, minus the coefficient of steel. Good. So this is what we have. Now we know Young's modulus for steel. The Young's modulus for steel is equal to 20 times 10 to the power 10 Pascal. Okay, so this is what we are looking at now. This is what we are looking at now. Good. So let's just factor in all our parameters and then let's solve, and then we are good to go. So this will be equal to 20 times 10 to the power 10 times the change in temperature, 140 minus 20, multiplied by, it's a continuation, multiplied by the change in linear coefficients, which is 2 times 10 to the power negative 5 minus 1.2 times 10 to the power negative 5. Great. So when we solve this, this should give us 1.92 times 10 to the power 8 Pascal. So this is the stress,